faculty members who are working in different fields of physics, frontline physics areas, in the condensed matter physics, nuclear and particle physics, cosmology, astrophysics, atomic and molecular physics, complex systems, and so on. And at present, we have 35 PhD students. The department is supported by DST under this DST FIST scheme.
Okay.
And we have a large number of sponsored projects which are either completed or ongoing. And we run integrated MSc program. Apart from that, we also run minor in physics program, especially for BE students. And we also run this PhD program. So without being an eclipsing object between the audience and the speaker, I invite Professor Diptiman Sen to present today's talk. Over to Professor Diptiman Sen.
Thank you very much for introducing me to your department. I have actually never visited BITS Pilani, so it was nice to hear about the activities going on there. So thank you also for inviting me to give this talk. So I have to apologize in the beginning that this is a talk that I first gave about 5 years ago, 5.5, just after this Nobel Prize was announced. And I have not changed the talk. So some of the things are maybe a little bit...
No problem.
Yeah,
we are eager to hear it.
some things are dated in this talk. Okay.
Yeah.
So by the way, let me just go back. So at the bottom there is my email. So if anyone has any questions, you are welcome to email and I'll try to answer the questions. Also, even during the talk, if you have any questions, please do ask because I'm happy to answer questions. Okay, so the Nobel Laureates who got the prize that year are Thouless, Kosterlitz, and Haldane. And the Nobel Prize cited theoretical discoveries of topological phase transitions and topological phases of matter. So what I'll do is I'll tell you about the work of these three people. First, I'll tell you about the work of Thouless and Kosterlitz, and then about the work of Haldane. Now, I want to begin on a kind of amusing note, which is that all the work that I will talk about are either in 2 dimensions or in 1 dimension. So even though we live in 3 dimensions, it turns out that a lot of interesting things can happen if a system is in 2 dimensions or 1 dimension. What that really means is that even though the world is 3-dimensional, the electrons can only move in 2-dimensional, or they can only move in 1 dimension. So it turns out this is an amusing thing from history that in 1884 somebody wrote a book called Flatland, this person Edwin Abbott, who actually was wondering what the world would look like to someone who was really living in 2 dimensions, which he called flatland, or somebody living in 1 dimension, which he called lineland. So he pointed out in this book that there are a lot of peculiarities which are there in low dimensions. For example, if you're in lineland and you're only able to move in 1 dimension, then particles can only move to the left or to the right. And if there's a particle A which is to the left of particle B, it will always stay on the left of particle B if you don't allow them to cross each other. Okay, so the ordering of the particles get completely fixed if you're in 1 dimension. Similarly, in flatland, which means in 2 dimensions, there are peculiarities like the following, that suppose you take a closed curve in 2 dimensions, then either a point has, given any point, either it has to be inside the closed curve or it has to be outside the closed curve. And if it's not allowed to cross this curve, it will always stay inside or always stay outside. So once again, the position of the particle with respect to this closed curve is fixed for all times to come. Okay, so this was just a very quick introduction to lineland and flatland. The next thing I wanted to say is, what is topology? So topology is a branch of mathematics. That's how it started, where we study those properties which remain the same if you make some small changes in the properties of the system. Okay, so an example is, suppose you take a surface and let's say it's connected. That means it doesn't have several disjoint pieces. It's one single piece, one single surface. and orientable, which is a little harder to explain, but it basically means that you can draw a perpendicular to any point on the surface, and as you go around the surface, and you come back to the same point on the surface, the perpendicular will come back to the same perpendicular. It will not flip sign. So suppose you have a connected and orientable surface, then the genus is the maximum number of cuts that you can make along some closed curves without making the surface fall into different pieces. So let me give an example straight away. So genus 0, for example, is a sphere. The reason it's genus 0 is that if you cut it with one single curve, a closed curve, let's say along the equator, then immediately the sphere falls apart into two separate pieces. Then genus 1 is the surface that I'm showing in the middle. This is genus 1 because if you cut it with just one closed curve, it will still not fall apart. But if you cut it with two closed curves, okay. Can you see my cursor, by the way, now? I don't know if the cursor is visible.
Yes.
So if you cut it with two closed curves, one like this and the other like this, then it will fall apart into two pieces. But if you only cut it with one curve, it will not fall into two pieces. And similarly, you can have genus 2, genus 3. So in common language, the genus of a surface is just the number of holes in it. Okay. So here's a cartoon. We see objects of different genus in daily life. In South India, we are very familiar with idli, which is genus 0, and then vada, which is genus 2, 1, and so on. Okay. So now the next thing I want to talk about is a concept called topological invariant. So topological invariant is a number which is, first of all, it has to be an integer, and it remains the same under small changes. And I'll explain what I mean by small changes now. So consider an example that suppose there is an origin, which I'm showing here, is the point labeled as 0. And then there's a curve which does not pass through that point. Okay. Now, the number of times this closed curve goes around this special point, the origin, in the anticlockwise direction, that's called the winding number. And it's a topological invariant in the following sense, that if you deform this curve a little bit, so you can deform it any way you like, but it should not pass through this origin at any time. So if you just deform it a little bit, the winding number remains the same. So for this curve, for instance, the winding number is +1 because it's going around this point 0 in the anticlockwise direction once. This is a curve where the winding number is -1 because it's going in the clockwise direction. Here's a curve which is again winding number 1, but you can see that it's getting more and more complicated to decide, right? The fourth one is not really obvious immediately what the winding number is. And the fifth one is even harder to immediately see what the winding number is. The last example is actually a curve with a winding number +2 because it winds around this point 0 twice. Okay, so the winding number actually is something that can have any integer value, and it can be both positive or negative because it is defined in a particular sense. It's positive if you go around anti-clockwise and negative if you go clockwise. Okay, now let me see. The important thing about a topological invariant is that it cannot change slowly if you make small changes. Like in the previous slide, what I showed you is this closed curve. As I said, if you change the closed curve, deform it a little bit, the winding number will not change. And that's the very important property of topological invariants. And it means that you can characterize a physical system by saying what the topological invariant of some property of that system is. Now, the only way a topological invariant can change is if it becomes ill-defined at some point. So here's an example. So on the left, we have this curve which has a winding number of +1 because it goes around this point O or 0 once. Then suppose I start moving this curve slowly to the right. Then at some point, this curve will pass through this point 0. And exactly at that point, the winding number is not well defined because it's passing through 0. But if you move the curve a little bit more so that it has crossed 0, and then now it's lying in a place which does not enclose 0, Now the winding number is 0 because it's not going around this point. So you can see here that the winding number has changed from 1 to 0, but the way it changed is that at one point in the middle, it became ill-defined. So that's the only way a topological invariant can change. It has to become ill-defined somewhere in between. So it is an invariant, but you can change it only if something special happens to the system. Okay, and we'll see what that special thing is. Here it's just the fact that the curve goes through that point or not. But in condensed matter physics, something else has to happen. So this was an example of a winding number of a topological invariant in one dimension, which is a winding number. The next example is a topological invariant of a surface. So for a surface, the one possible topological invariant is how many times let's say you take two spheres, how many times the surface of one sphere, let's say the red sphere, how many times does it wrap around the surface of another sphere, which is shown in blue, in 3 dimensions. So again, let me give you an example. Here is a red sphere on the left. It's a very small sphere, and you can see that it's not really wrapping around the blue sphere at all. And in fact, you can contract this red sphere slowly and make it very small so that it doesn't even go anywhere near the blue sphere. So this will call the wrapping number to be 0. Here's a case where the red sphere wraps around the blue sphere exactly once. So there's a 1-to-1 mapping between points on the blue sphere and the red sphere. So this is called wrapping number 1. Here's a case where this is harder to visualize. The red sphere actually wraps around the blue sphere twice. So you have to imagine that as you go around the blue sphere, the red sphere, you're going around twice. So this is wrapping number 2. So I'm actually trying to avoid very mathematical expressions. But just like the topological invariant in one dimension is called the winding number, here this wrapping number is actually technically called the churn number. So it's a topological invariant defined for surfaces. And it tells you how many times one surface wraps around another surface. And it's called the churn number. So incidentally, there are mathematical formulas for finding the winding number of a given curve or the churn number of a given surface. I'm not showing those formulas here, but there are well-defined mathematical formulas. So you don't have to guess by looking at the picture what the wrapping number or winding number is. You can actually calculate it. Okay, the next thing I want to tell you about is phase transitions. So a phase transition is a qualitative change in the properties of a system. A qualitative change, which means something basic changes in the system. So it can change, the change can happen due to temperature. So for example, you can go from ferromagnetic to paramagnetic or solid to liquid. Or it can happen because changing pressure, or you can apply a field. If you apply a magnetic field, you can go between a normal metal and a superconducting system. Phase transitions can also be first ordered or continuous depending on whether the change is sudden. Example being melting of a solid to a liquid, or continuous. So example being a ferromagnet changing to a paramagnet, where the magnetization changes continuously as you go across the phase transition. So let me now talk about continuous phase transitions. So it turns out that a large class of continuous phase transition, they involve the breaking of some symmetry. For instance, if you take a magnetic system, there is a critical temperature called Tc, below which the magnetization is non-zero. So below the critical temperature in the magnetic system, let's say all the ions which carry spin, they all point in some direction, and they give a total magnetization which is not zero. Now the magnetization is a vector, so in principle it can point in any direction in space, but the free energy of the magnet would be the same no matter which direction the magnetization points. So that is the symmetry of the system, that the magnetization could point in any direction and you'll get the same free energy for the system. However, if you take one particular magnet, you'll find that in it, the magnetization has points in one particular direction. So this we call spontaneous breaking of symmetry, that even though initially we were allowed to have the magnetization point in any direction, one particular sample will only have magnetization pointing one direction. So this rotational symmetry, the symmetry that it could point in any direction, is broken, and you have magnetization only in one direction. So we are talking about a continuous symmetry. You can also have systems with discrete symmetry, but let me skip that. Let me just pause. Are there any questions at this point from anyone, students particularly? Okay, probably not. So to continue, so for a continuous phase transition, we can define something called an order parameter, and which tells us whether we are in the ordered phase or in the disordered phase. So for example, in a magnetic system, the order parameter is the magnetization. And if you plot it versus the temperature, it will take some non-zero value at temperatures below Tc. So this blue curve is the non-zero value of the order parameter in the ordered phase. Above Tc, we have the disordered phase, and everywhere there, the magnetization is zero. And you can see this is called a continuous transition because its magnetization smoothly goes to zero as you approach Tc from below. And above Tc, of course, it's zero. Okay, so this is the concept of an order parameter. And now here's a cartoon of disordered and ordered phases. So in the disordered phase, this is what you'd get if you're above Tc. So there are different, so magnetic system has different ions which point in, whose spins point in different directions, random directions, so that the total magnetization of this system is zero. So this is called the disordered phase. This occurs above the critical temperature. The ordered phase, which occurs below the critical temperature, all the spins point in the same direction. Now, this is of course not exactly true. There are still fluctuations. Spins can point a little bit away from the preferred direction, but on the average, they point in a particular direction so that the net magnetization of the system is not zero. Okay, so this is the concept of disordered and ordered phases. The next thing is to talk about critical exponents. So it turns out that there are many critical exponents which are associated with the continuous phase transition, in which symmetry is spontaneously broken. So for instance, if you look at this order parameter m that I talked about in the 2 slides earlier, the thing that continuously goes to zero as you increase the temperature across Tc, it turns out that when you approach the critical temperature from below, the magnetization goes to zero as Tc minus T to some power beta. Beta is a positive power, so that m goes to zero as temperature approaches Tc. So beta is an example of a critical exponent. Similarly, there is a critical correlation length xi, which is defined. If you look at the correlation function of the magnetization, the local magnetization at 2 different points, let's say R1 and R2. So this is these symbols mean, this left and right symbols mean the average value at a finite temperature. Typically, this will decay exponentially if you're above Tc. Even below Tc, it decays exponentially provided you subtract out the square of the average value. Now, the decay happens over a length scale which is called xi, that's called the correlation length. And you again find that this also this diverges as we approach the critical temperature from either side. So xi goes as Tc minus T to some minus nu, and then this nu is another critical exponent. So by the way, the important thing about critical exponents, beta, nu, and the other exponents, is that they are universal, that all kinds of systems which are described by one particular idea, that means a particular kind of order parameter, a particular dimension of space, the symmetries and so on. Once you have specified all this, then it doesn't matter which system you take, which sample, which material, they will all have the same values of the critical exponent. And that's why people are so interested in calculating critical exponents or experimentally measuring them. Now, the question is, can you have phase transitions in any arbitrary dimensions? So it was shown a long time ago. There's a famous result by 2 physicists, Mermin and Wagner, in 1966, that a continuous symmetry cannot be spontaneously broken at finite temperature for 2-dimensional systems. Okay. So without going into any mathematical details of this, the argument they gave is that at any finite temperature, there will be excitations with very low energies, and they will be excited in large numbers, which will disorder this system. In other words, you can start the system off in a state where all the spins point in the same direction. But then there will be these excitations which start making the spins point in random directions. And at any finite temperature, there will be a sufficient number of excitations which will manage to completely disorder this system. Now, what are these excitations which disorder this system? So in a magnetic system, these excitations are spin waves. Okay, so these are excitations in which the direction of each spin is slightly different from that of its neighbors. I'll say maybe a little bit more about spin waves after a couple of slides. But what this theorem of Mermin and Wagner suggested was that there cannot be a phase transition at finite temperature in two-dimensional systems which have a continuous symmetry. So the work of the first two Nobel laureates, Thouless and Kosterlitz, in 1971-74, there was actually a third person, a Russian named Berezinskii, who also did similar work, in fact, even earlier than Thouless and Kosterlitz. But I guess he passed away before this Nobel Prize was given. So in a series of papers, these people showed that you can have a phase transition, even if the order parameter is two-dimensional, but it's a very peculiar kind of phase transition. So there's nothing wrong with the Mermin-Wagner theorem. What they showed is that you cannot have a breaking of a continuous symmetry. So you have to be in a disordered phase at any finite temperature. That's the Mermin-Wagner theorem. So what Kosterlitz, Thouless, and Berezinskii showed is that you can have a phase transition, but it's a peculiar phase transition in that it's between two phases which are both disordered. So it's unlike a usual phase transition, which is between an ordered phase at low temperatures and a disordered phase at high temperatures. In the Kosterlitz-Thouless transition, both the low temperature phase and the high temperature phase are disordered. So you'll immediately ask, how can you have a transition between two disordered phases? Okay, so let's try to see that. So the kind of system that they looked at is what is called a planar spins in a planar system. So by that I mean the following. First of all, planar system means the system is two-dimensional. So you can think of spins sitting at the points of a square lattice, for example, as I've shown here. Okay, so that's the planar system. The planar spins means that these spins can only point somewhere in the xy plane. So they're not free to point in arbitrary directions in 3 dimensions. For some reason, they can only point in the xy plane. In other words, they only have 1 degree of freedom, which is the angle they make with respect to the x-axis. You know, if you have a spin in 3 dimensions, it has 2 degrees of freedom. You can think of that as the two polar angles, theta and phi, that the spin makes with respect to the z, with respect to x, y, z. But for spins which can only point in xy plane, it's only got the angle phi, which is the direction it makes with respect to the x-axis. Okay, so here's a picture of a ferromagnet in 2 dimensions. Now, the spin wave excitations which can disorder this system are the following. Think of, so what I'm showing right now is a purely ferromagnetic configuration where every spin points in the same direction, shown by this arrow. But a spin wave is something where each spin is able to just turn a little bit away from its average position, and the amount by which it turns is different for different spins. So as you move along the x-axis, as you move in this direction, let's say every spin turns a little bit more with respect to its neighbor. So it's clear that if you go all across the system, so even if every spin turns a little bit, but the system is supposed to be infinitely large, so if you go completely across the system, then of course it will completely disorder it, these spin wave excitations. Okay, so this is the idea of Mermin-Wagner, that the magnetization is always 0 in an infinitely large system because of the spin wave excitations. However, it turns out that this system has another kind of excitation, which Mermin-Wagner had not thought about, which is topological in nature. So the spin system has excitations called vortex and antivortex. So a vortex is one where, so again, these arrows show the directions of the spin. So a vortex has kind of a preferred region. You can call that the origin of the vortex if you like. And then as you go around in a circle around that, the spins also go around. And this is called a vortex in the sense that the spins go around once as you're going around the origin once. So this is, if you like, this is kind of a winding number that we are talking about here. Now, of course, these spins can wind around in the anti-clockwise direction, as I've shown here, or they can wind around in the clockwise direction, which is a little harder to imagine. But here on the right is an example of an anti-vortex where they wind around in the opposite direction. So if you go around in a circle, you'll discover that the spins, as you go around the circle, they sort of wind around in the clockwise direction. So these have winding numbers +1 and -1, vortices and anti-vortices. Now, it turns out that a single vortex disorders the spins. And in fact, it disorders the spins much more than a spin wave excitation. The reason for that is that A spin wave excitation is, remember, it's just a small change in the direction of the spin. It's a local change. Of course, across the entire system, it changes the spins a lot, but in some small region, it only changes the direction of the spins a little bit. But a vortex changes spins everywhere throughout the system. So here's another example of vortex. It looks a little bit different from the previous one. But here, everything is pointing radially outwards, whereas the previous picture, they were kind of going angularly around the vortex. But otherwise, they're identical. So here's a vortex. This is the center of the vortex. And as you go around, you can see that the spins are always pointing radially outwards. So once again, if you went around, you'll find that the spins actually are turning anti-clockwise. So this is a vortex with winding number 1. But you can see from here that if you're very far away from the vortex, then the spins have got completely disordered in the sense that a spin very far to the right here and a spin very far to the top here, or a spin very far to the left here, they point in completely different directions. So vortices can also disorder the spins, and they do it much more efficiently than a spin wave excitation. Now, turns out, however, that it is very costly energetically to produce a vortex. So a single vortex costs a large amount of energy. So a little bit quantitatively, if you have a large system with dimensions L by L, some square system with dimensions L by L, the energy of a vortex is of the order of log L. So I have a small derivation of this here. Let me just go through this quickly. So here's a simple kind of expression for the energy in terms of this angles theta of the spins. So let's say the angle theta I is the angle made by the spin at site I with respect to the x-axis. So the energy cost, if two spins are not pointing in the same direction, is cos theta I minus theta j. So basically, if they point in the same direction, then they have the least energy minus j. But if they point slightly away from each other, the energy is slightly higher. Okay, so this is a reasonable kind of energy expression. It just tells you that spins like to point in the same direction, and there's energy cost if they point slightly away from each other. Now, in the ferromagnetic ground state, all the thetas will point in the same direction, so you'll have really the lowest possible energy, which is minus j times the number of spins. Now, suppose you have a vortex, then we have already seen that at a large distance r from the vortex, the relative angle between two spins will be of the order of 1 by r. So let me go back to this previous picture. So let's say you are at some distance from the origin. So this is your distance. You can see that as you go all around in one circle, the spins rotate by 2 pi. So if you only go a little bit, it rotates by 2 pi divided by the small, it rotates by just that small angle. And at a large distance, that small angle is equal to this distance divided by r. Okay. So the relative angle between two neighboring spins which are displaced in the angular direction is of the order of 1 by r. So this cos theta I minus theta j differs from the ground state value of 1 by 1 by r squared. Theta I minus theta j is 1 by r. So now we can calculate the total energy of the vortex. This is the integral over all of space of 1 by r squared. And if this r integral goes from a small distance a, which is the nearest neighbor spacing, to the large distance L, which is the size of the system, you can see that this goes as log L. Okay, so this is the reason I said that the energy vortex is log L. Okay, so unlike a spin wave, a vortex actually costs a very large amount of energy. So, so it looks like it's very hard to produce a vortex, because if you are at a finite temperature, kBt is your Boltzmann constant times the temperature. If the vortex energy is much bigger than kBt, then you will not produce a vortex. However, it turns out that even though a single vortex costs an energy which grows logarithmically with the system size, if you have a pair, a vortex-antivortex pair, this only costs a finite energy. And it does not change the spins everywhere. So here's a picture again. So the red region at the bottom is the vortex. The blue region above that is the antivortex. You can see around each of them separately, the spins do rotate by 2 pi, clockwise or anti-clockwise. So they certainly disorder the spins in their neighborhood. But if you're very far away from both vortex and antivortex, you can see all the spins are pointing down. So basically, the effects of vortex, antivortex cancel out if you are very far from both of them. Okay, So if a vortex-antivortex pair only costs a finite energy, you can produce such pairs at low temperatures. Because now, if you are at any temperature kBt, you only have to produce an excitation which is the energy of the vortex-antivortex pair. So the probability of that will be some Boltzmann factor e to the power minus delta E by kBt. Okay. Now, so at low temperatures, you can get these pairs of vortex-antivortex, but at high temperatures, you can also get single vortices. Now, even though they cost a lot of energy, single vortices, you can get them because there's an entropy associated with the vortex. Okay, so again, I'm going to do a little calculation here. Suppose you have a system with dimensions L by L. The vortex can be centered around any one of those sites. The number of sites is L by A squared. A is the lattice spacing. So if each side of the system is L, then the number of lattice sites in each direction is L by A. So the total number of sites is L by A squared. Now the entropy of vortex is therefore, this is Boltzmann's famous formula. The entropy is Kb log W, where W is the number of states available. And so this is Kb log L by A squared, so twice Kb log L by A. Okay. So now there's a competition between the energy and the entropy of a vortex. So if you're at a finite temperature T, the free energy of a single vortex is the energy of the vortex minus T times the entropy of the vortex. So it's the energy we just saw is pi j log L by A, and then the entropy is 2 kb log L by A. So now you can see that which one wins depends on your temperature. If the temperature is smaller than pi j by 2 kb, then the free energy is minimum if there are only single vortices. If there are no single vortices. So what I'm saying is if T is small, then this is small compared to that. So there'll be an energy cost if you have vortices. So you'll not have vortices, but you can have vortex-antivortex pairs. But if the temperature is large, then this comes with a negative sign. So it is then favorable. It's favorable to have lots of vortices because that will lower the free energy. So there's a critical temperature called the Kosterlitz-Thouless critical temperature, which is pi j by 2 kb, such that the system is more disordered above the critical temperature than below. Note that it is always disordered. So this is the point about the Kosterlitz-Thouless transition. It is a transition between two phases, both of which are disordered. But the difference is that at low temperatures, you get only a vortex-antivortex pairs, lots of them, but no single vortices. At high temperatures, you get lots of single vortices. Okay, so let me say that again. So we have two disordered phases. At all temperatures, the system is disordered and the magnetization is 0. However, the amount of disorder is less below the critical temperature than above the critical temperature. So it turns out that below the critical temperature, the 2-point correlation function goes to 0 only as a power. So this, of course, needs a lot of work to prove. So this is what Kosterlitz-Thouless proved, that the correlation function, instead of going to 0 exponentially, if it went to 0 exponentially, that would mean there's a correlation length. But it doesn't go to 0 exponentially. It only goes to 0 as a power. So the correlation length is actually infinity. But the power with which it goes to 0, it depends on the temperature. So that's another interesting thing about this phase below the critical temperature, that you have a power law which varies smoothly with the temperature. Above critical temperature, of course, the correlation decays exponentially. So there is a correlation length. But interestingly, as you approach the critical temperature from above, this correlation length grows very, very rapidly. It grows much faster than any power law. So this Kosterlitz-Thouless transition is really peculiar in many ways. Below that temperature, correlations only fall as a power law, but the power changes with the temperature. Above the critical temperature, correlation length diverges very quickly as you approach critical temperature, much faster than a power law. Okay, let me skip this. Maybe I'll skip both of these. Okay, so so this I have to discuss. So another quantity that changes suddenly across the Kosterlitz-Thouless is something called the spin stiffness, which is the following. Suppose you put a small twist on the spins. So what that means is that, let's say physically, you force the spins to rotate a little bit as you move across the system. So this angle theta, remember, is the angle made by a spin with respect to the x-axis. So suppose theta of r, you force it to be theta of 0 plus k dot r. So as you are moving from 0 to r, the spins are rotating. Then it turns out, suppose this costs a free energy, that this f, it's a function of this k, right? So this is f of 0 plus half a rho k squared. So there's an energy cost to this twist. And the energy cost is proportional to the area of the system, first of all, and then proportional to k squared. And then this factor in between is called the spin stiffness, rho. So it turns out that the spin stiffness is non-zero below the Kosterlitz-Thouless transition temperature and 0 above. So basically what it means is that below the Kosterlitz-Thouless transition temperature, it's not easy to rotate the spins. Even though they're disordered, but they're only disordered with up to power laws. So they still resist twisting. On the other hand, above the Kosterlitz-Thouless transition, this thing is disordered very badly, and there is no energy cost to twisting the spins. It's very easy to twist the spins. So the spin stiffness is 0 above the Kosterlitz transition. So when the temperature crosses this Kosterlitz-Thouless transition, there's a universal jump in rho. By universal jump, I mean it only depends on the Kosterlitz-Thouless transition temperature. It doesn't depend on any other details of the material. Okay, so let me just tell you about an experimental observation of this, because this is very important. Every theory has to be backed up with some experimental observation. So now I gave you the entire description in terms of spins which are only free to rotate in the xy plane. But this Kosterlitz-Thouless transition will happen in any system where the order parameter is two-dimensional. It doesn't have to be the direction of spin. It can be something else. For instance, you can have a superfluid. So in a superfluid, the order parameter is the wave function of the atoms which form the Bose-Einstein condensate. Or in a superconductor, the order parameter is the wave function of the Cooper pairs of electrons. So remember that these wave functions in a superfluid or superconductors, they're complex numbers. So they have a magnitude and they have a phase. So it's the phase that is the order parameter. So the phase can go from 0 to 2 pi. And so that's the order parameter. That's just like the direction of the spin in xy plane. Okay, so the magnitude of the wave function turns out cannot vary much because that costs a lot of energy, but the phase can vary more easily. So it plays the same role as the orientation of the planar spins in the model that I told you about earlier. And now in a superfluid, a vortex is a region where the superfluid rotates around some point. So that's the physical mechanism of a vortex in a superfluid, that this fluid actually goes round and round. It's just like the vortex that you'll see in your kitchen sink when the water goes down from the tap into the sink. Typically, it will have some rotation, which you can see. So it turns out that what I told you earlier is the spin stiffness of a spin system. But in a superfluid, the equivalent of the spin stiffness is rho, which is related to the superfluid density, rho s, multiplied by Planck's constant square divided by the m squared, the mass of the atoms forming the superfluid. For instance, if you have a superfluid of liquid helium-4, m is the mass of a helium-4 atom. So here is some data from 1978. So what is being shown here is the critical temperature, or the Kosterlitz-Thouless transition temperature on the x-axis. And the y-axis is this jump in the superfluid density just as you cross the critical temperature. And the prediction from the theory of Kosterlitz-Thouless is that this is the jump. This is this universal jump in the system. Now, the different data points actually correspond to different thicknesses of the sample. So I forgot to tell you, this has to be a two-dimensional system, right? Because that's the only system that will show a Kosterlitz-Thouless transition. So what they actually do is they take a superfluid, but make a very thin film of it so that it's almost two-dimensional. If it's very thick, it's three-dimensional and you'll not see this transition. So you make a thin film of a superfluid, but this film could have different thicknesses. So different thicknesses are different samples. So you can have different phase transition temperatures depending on the thickness of the sample. But no matter what sample you take, you find that this relation between this jump in the superfluid density and the Kosterlitz-Thouless transition, it's a straight line. And it agrees quite well with this theoretical prediction. Okay. Thouless did something else in the quantum Hall effect, but I think I'll skip that because I don't have time for that. Okay, so let me now come to the work of Haldane. So remember, there were three people who got the Nobel Prize. The first two, Kosterlitz, Thouless, got it for discovering this Kosterlitz-Thouless phase transition, which can happen in two-dimensional systems when your order parameter is also a two-dimensional object. Now I'll talk about the work of Haldane, who studied spin systems in one dimension. Okay, so imagine that you have spins which are located at the sides of a lattice in one dimension. Now it turns out the value of the spin depends on the system. So if you have a system which has copper 2+ ions, that has spin half. If you just look at the atomic orbitals of copper, you'll find that copper 2+ basically has just one unpaired electron, so it has spin half. Whereas if you take nickel 2+, it turns out to have two unpaired electrons pointing in the same direction because of Hund's rule, so it has spin 1. Okay, so suppose that spins on neighboring sides in this one-dimensional lattice have Heisenberg interactions of the antiferromagnetic form. By that I mean that there's a Hamiltonian like this is J times Sn dot Sn plus 1. This is nearest neighbors n and n plus 1. And the coefficient in front J is positive. So this is called antiferromagnetic because classically, if these spins were classical spins, they would like to point in opposite directions between nearest neighbors, right? So they would like to point up, down, up, down, up, down, because that will give a negative sign. Sn dot Sn plus 1 would be negative, and that will minimize the energy of this Hamiltonian. So this is called the antiferromagnetic configuration, sometimes also called the Neal state. However, it turns out that if you do a quantum theory of this, the spins are really quantum objects. For spin half, the spin is really h bar into Pauli matrix by 2. They don't commute with each other. So the system is not as simple as I've shown here, and in fact the state, the Neal state that I've shown here is no longer an eigenstate of the quantum Hamiltonian. So, so what do the excitations look like in this system? So again, this is actually a very old subject, and for a spin half antiferromagnetic chain, the energy spectrum was found exactly by Bethe in 1931 by something called the Bethe ansatz. I mean, he made a guess for what the eigenstates of the Hamiltonian should be. And using that guess, he was able to find all the eigenstates. So this actually, the spin half antiferromagnetic chain turns out to be a completely solvable problem. You can find all the energy levels and eigenstates. So the ground state has a total spin 0, it turns out, and the excitations are gapless. So this picture actually shows you the excitations, omega, h bar omega, but I've just written omega, divided by j, which is the coefficient of in the Hamiltonian. So omega by j is in the y-axis, and the x-axis is the momentum of the spin wave. Okay, so we are talking about a spin wave here. And the q goes from 0 to 2 pi. So I'm assuming that the lattice spacing is 1. So q only goes from minus pi to pi or 0 to 2 pi. Okay, so the important point to notice is that the spin wave spectrum goes to 0 at q equals 0 and pi. Okay, so this is called a gapless spectrum. There's a lot of interesting structure here that it turns out for every q there's a whole range of energies that the spin waves can take. But for our purpose, the important thing is that omega does go to 0 at 2 values of q. So this is for spin half. The opposite limit, where the spin is very large, much bigger than 1, was studied by Anderson in another famous paper in 1952. And Anderson showed that the ground state of an antiferromagnetic chain again has total spin 0, and the excitations are gapless. They basically look like this lower part of this curve. Okay, good. So Bethe showed that the antiferromagnetic spin chain is gapless for spin half. Anderson showed that it's gapless for large spin. So the guess that people made was that maybe this is true for any value of the spin. Spin 1, spin 3R, spin 2. They'll all be, this excitation, spin wave excitation will all be gapless at some value of the momentum. So the Haldane's great contribution was to show that this is not true. So again, he wrote a series of papers in 81, 83, using techniques from relativistic quantum field theory. So this is actually a really technical subject. And there's an interesting history here that very few people initially believed Haldane's result, and his original paper was actually rejected in 81. Now, here I have to apologize. You see, I gave this talk 5 years ago. And when I gave this talk, just a week before that, Haldane posted his original paper on the archive. So this is the archive. This is the archive version of his paper. You can take a look at this because the version published in the paper may be not possible to download. But you can look at this and to see the original Nobel Prize winning paper. So even though it was rejected by the journal in 81, it was eventually published in 83. So he showed that antiferromagnetic spin chains with integer spins like s equals 1, 2, 3, etc. have a gap between the ground state and the spin wave excitations, whereas chains with half-odd integer spins, half, 3/2, etc. have gapless excitations. This was a prediction, it's quite brilliant. It was a completely theoretical prediction using techniques from quantum field theory. And it was confirmed only later numerically and then experimentally, which I'll tell you about. So numerically, it was confirmed that this is what the spectrum looks like for spin 1. So the ground state is here, right at the bottom. Everything is being measured with respect to the ground state. So you can see that the first branch of spin wave excitations is this one, right? It actually has the lowest value at q equal to pi, and then it goes up and then comes down. It has twice the value at q equal to 0. And this branch, these spin waves have spin 1. Then it turns out you can form bound states of the spin 1 and you can get spin 2 that way. You can get bound states of 3 spin waves and you can get spin 3 and so on. But the important thing is that the lowest energy of a spin wave is separated by a gap from the ground state. So in fact, the gap is 0.41 times the J, that the parameter that appears in the Hamiltonian. Okay, so I think I'll actually skip the derivation that Haldane gave because it's actually quite technical. But let me show you the experimental observation. So, after getting the Nobel Prize, Haldane was, of course, interviewed by journalists who wanted to know the history of this. And he made this nice statement that even though his papers were rejected in the beginning and many people, even theorists, did not believe his work, he said there's nothing like experimental confirmation to quiet the critics. So here's the experimental confirmation. It was actually confirmed long ago, very soon after, just a few years after Haldane's prediction. But I'm showing you data from a more recent experiment, 2002. So this data is found from neutron scattering experiments on a spin 1 chain. So notice that this has nickel. So as I said, nickel 2 plus has spin 1. So this is a chain of this molecule. But the important things in this chain are the nickel 2 plus ions. Those are the ones which carry spin. The cesium and chlorine are not important from the spin point of view. What is being plotted here is the energy of the spin waves as a function of their momentum. So the momentum is shown in reciprocal lattice units. So units of 1 over the lattice spacing. The way the experiment is done is that you bombard the system with neutrons and the neutrons get scattered. So this is a standard thing. You like to bombard with neutrons because they're charge neutral. So they don't have Coulomb repulsion from anything. So they can easily penetrate the system, and then when they go and scatter off the spin waves, knowing the initial and final energy and momentum of the neutron, the difference will tell you the energy and momentum of the spin wave from which they scattered. So here's the plot of the energy of the spin wave versus its momentum, and you can clearly see there's a gap. It doesn't go to 0 anywhere. The minimum value it has is 1 in this reciprocal lattice units. So just for curiosity, the temperature was 6.2 Kelvin and the incident energy of the neutron was 30 MeV. And the energy of the spin waves lies in this range, roughly 2 MeV to 6 MeV. Okay, so this is a very clear picture showing that there is indeed a gap between the ground state and the spin wave excitations in a spin 1 chain. Another way to check this out, is there a gap or not, is to look at the magnetic susceptibility. So if the excitations have a gap, delta, the magnetic susceptibility will very quickly go to 0 at low temperatures as chi will goes e to the minus delta by kBt. So this is just because of the Boltzmann factor that to have an excitation across an energy gap of delta, the probability is e to the minus delta by kBt. So this is found to be the case in the same kind of system. Not exactly the same, but it's still nickel. So it's still a spin 1 system. And here's a different experiment from 2008. So you can see this chi. At higher temperature, it seems to follow the Curie law, right? Chi goes as some power 1 by T or something. But at low temperatures, it bends down and it goes to 0 exponentially. And so that's the signature that you do have a gap. You only see it at low temperatures because you have to go to temperatures lower than the gap before you start seeing this exponential drop-off. So there's some more things. Okay, let me now ask how many minutes do I have? So depending on that, I can say something more.
How many slides you want to cover?
Okay. Uh, okay. Maybe about 5 or so.
It's okay. Okay, you
Okay,
can
that's fine. Yeah.
go
So
ahead.
it'll take about 10 to
Yeah,
15
no.
minutes. Okay, so this is, no, so this I'll skip. I want to say something else. Um, so, um, so these are almost the last words, but I do have other things to say after this. So one of the important things about the work of these three people, Thouless, Kosterlitz, and Haldane, is that they introduce new ways of thinking about old problems. This is very important if you want to do really important work. That it's not necessary that you always work on what is fashionable. You can work on old things, but you have to think about them in a new way. Otherwise, you'll not get any new results. So the work of these three people is a perfect example of that. So their work actually overturned some conventional wisdoms. For example, the Kosterlitz, Haldane, Thouless Kosterlitz work overturned the wisdom that phase transitions are not possible at finite temperature in two-dimensional systems with a continuous symmetry. They showed that you can have a phase transition. It's just that it's a different phase transition. It's between two disordered phases rather than between an ordered phase and a disordered phase. But you can have a phase transition even in two-dimensional systems with a continuous symmetry. So that was the revolutionary thing about Thouless and Kosterlitz. Similarly, Haldane showed that the conventional wisdom for spin chains, antiferromagnetic spin chains, was that it should have gapless excitations, spin wave excitations for any spin. And Haldane showed that that's not true. For integer spins like spin 1, spin 2, etc., you will have a gap between the ground state and the spin wave excitations. And in fact, that's now called the Haldane gap. So sometimes it helps if you don't know too much about what was known earlier. So Kosterlitz said at some point that his ignorance of the conventional wisdom was an advantage because he didn't know that you're not supposed to have a phase transition in two-dimensional systems. Now, let me say a few things about modern developments. So the work of the Nobel Laureates inspired a huge amount of research on topological aspects of condensed matter systems. So, some systems have topological and non-topological phases which are separated by continuous phase transitions. In fact, the Kosterlitz-Thouless transition is sort of like that. Below that temperature, you don't have vortices which are topological. Above that temperature, you have single vortices. They are topological because they have a winding number. Okay, so what is a topological phase? A topological phase has the following properties. The bulk of the system should be gapped. So there should be a finite energy gap between the ground state and the excited states. So the bulk is an insulator at low temperatures. But secondly, the band structure of the bulk of the system should be characterized by a topological invariant, which is some non-zero integer, which is very robust, as I said. If you change the system a little bit, if you introduce a little bit of disorder or change the lattice structure a little bit, the topological invariant should not change. Okay, so the bulk is gapped and the bulk bands are characterized by a topological invariant. But now comes the next thing about a topological phase is that there are gapless states at the boundaries of the system. And because those are gapless, by gapless I mean there are states at the Fermi energy of the system, at the boundaries. So they can contribute to the electronic transport or thermal transport. And the most important thing is that there's a correspondence between the bulk properties and the band and the boundary properties. So there's something called a bulk boundary correspondence, which is that the number of boundary states is equal to the topological invariant. So it doesn't change if the parameters in the Hamiltonian are changed a little bit or if a small amount of disorder is present. So let me just, couple of more slides. So an important thing about systems in a topological phase is that there's no local order parameter. So unlike magnets, superfluids, superconductors, there's no local order parameter. You can't look at a little piece of a topological phase and say that this is in a topological phase rather than a non-topological phase. Okay, you have to look at the entire system. You have to look at the edges of the system to figure out whether it's topological or not. If it has edge states, it's topological. If it does not have edge states, it is not topological. But you cannot say this by just looking at a little bulk piece of the thing. So the topological invariant is what is called a global quantity. You have to know the band structure for all values of the momentum, and you can only calculate the topological invariant if you know about the full band structure. Now, of course, as a parameter in the Hamiltonian is changed, you can make a phase transition from topological to non-topological. This is a continuous transition. As I said, the only way you can have a continuous transition between topological and non-topological is if something goes wrong at the transition. So what happens here is that exactly at the transition, the bulk of the system becomes gapless and is therefore no longer an insulator. So the topological invariant becomes ill-defined at that point. Okay, so now let me just quickly mention, I'm very close to the end. So I'll mention 4 different examples of topological phases. So the first example, which is also historically the first example known, are quantum Hall systems. So these are 2-dimensional systems of electrons in the presence of a strong magnetic field. So the electrons, they are constrained to move in 2 dimensions. So these are typically heterostructures of gallium arsenide and gallium aluminum arsenide. They have different band structures. So when you have an interface of these 2 things, there is a narrow region where the electrons are trapped because the energy there is lower than the energy in the 2 different sides of that interface. So they're trapped to move in that 2-dimensional interface. So that's what makes them 2-dimensional. And then it turns out that only the edge states of that 2-dimensional region contribute to the Hall conductance. And in the quantum Hall system, this Hall conductance sigma xy. So sigma xy basically is the following. You apply a voltage difference in, let's say, along the x direction, then you discover there's a current which flows in the y direction. So it's a transverse conductance. So in the quantum Hall system, the sigma xy is quantized to be an integer or a fraction times e squared by h. For an integer quantum Hall effect is given by something called a TKN invariant, which I didn't get a time to talk about. It was there in an earlier slide. By the way, I'll be happy to send you this slide, this whole talk, and you can look at it more in a more leisurely way. So TKNN was, there were 4 people, Thouless, I think Dennis, and 2 other people. So Thouless played an important role even in this quantum Hall system. So it turns out this is actually a Chern number. This is an example of a Chern number because it's a 2-dimensional system. So for the integer quantum Hall effect, the sigma xy is given to be a topological invariant. It's an integer. And because it's an integer, it doesn't change if you introduce a small amount of disorders. So quantum Hall systems are wonderful. They are disordered. They can be slightly disordered. You can even have a small amount of temperature, but the conductance will still be exactly quantized to be a multiple of e squared by h. Okay, so E is charge of the electron and h is 2 pi h bar. So quantum Hall systems were the first known examples of topological phases. The next example I want to mention is 2-dimensional topological insulators. So these are 2-dimensional systems, again, trapped at some interface, and they have states at the edges which contribute to both charge and spin transport. So the number of edge states is again given by a topological invariant, which is now, in this case, is a wrapping number, but it's also a Chern number. Then there are also, it turns out, 3-dimensional topological insulators. Now, here the bulk is 3-dimensional, and topological insulator means that the bulk is gapped. There are no states in the bulk which lie at the Fermi energy. But there are gapless states at the surfaces, and the number of surface states is either even or odd. So again, this is given by a topological invariant. In this case, the topological invariant can only take 2 values, 0 or 1, and depending on that, the number of surface states is even or odd. So there are lots of examples of this system, bismuth selenide, tellurium selenide, which are extensively studied and has been studied actually for the last 10 years or more. Okay, so you can have topological insulators in 2 dimensions, 3 dimensions. Interestingly, you can even have them in 1 dimension. So there is, you can form superconducting wires, quasi 1-dimensional. They have a little bit of width, but they're much longer than they're wider, and they have to be p-wave. So you need a special setup to make these systems, because p-waves by themselves are not easy to produce. So what they have to do is they have to take a wire which has strong spin orbit coupling, and then they put that next to a S-wave superconductor, and then somehow the combination of a spin wave or coupling and S-wave turns it into effectively p-wave. Now this is a 1-dimensional system, so the boundaries of this are the ends of the system, right? So again, you have these boundary modes, but they now sit at the ends of this system, and they have 0 energy. And so the number of these modes is another topological invariant, which is, again, it turns out to be a winding number. Most interestingly, these behave like half an electron. So these modes, the funny thing about them is normally if you study electronic systems and sort of advanced condensed matter physics, you know that you have to deal with creation and annihilation operators for electrons. The annihilation operator for electrons, A, is the Hermitian conjugate of the creation operator A dagger. But for Majorana fermions, it turns out there's no difference between A and A dagger. Their operators A is equal to A dagger. So in that sense, they are sort of like half an electron. They only have one half of creational and annihilation operators. Okay, I didn't say anything in detail there, but they're called Majorana fermions. And a few years ago, there was a lot of excitement because there was an experimental group in Delft University in the Netherlands which claimed that they had seen signatures of Majorana fermions at the ends of one of these superconducting wires. But there's some controversy whether they actually saw Majorana fermions or something else. Okay, so I'll stop there. So I'll end with references. So here are some articles which are written at a fairly popular level. The first two are really written at a popular level that you can look at. And the last one is a little bit more advanced. They were put up by the Nobel Prize committee itself. So you know that they'll have all the facts given correctly. So let me stop there. And I'll be happy to take any questions.
Okay, so thank you very much for nice presentation of this very complicated aspect. So I
Thank you.
invite audience, if you have any question or anything, you just raise your hand in the Google Meet. I will pass your queries to the speaker. Yes, any of you?
Okay.
Yeah, it seems there is no query or question.
That's fine. Yeah.
Just one query.
Yeah, Naveen, Professor Naveen Singh. Yeah.
Hello, Professor Diptiman. It was a nice talk.
Okay, thank
I
you.
just would like to understand the basic logic means for integral spin and half, how these phase transition are getting affected, means that the theory which, if I understood it correctly.
The Haldane's theory. You're asking about the Haldane's theory of the antiferromagnetic spin chain? Let me just go back.
Yeah, this picture, yeah.
This picture. So why is there a difference
This
between
theory.
the spin half and spin one? Okay, so
Yeah.
it turns out that this is a little bit complicated, but since you have asked, let me try to say something at least. It's an example of a quantum field theory, but
Okay.
let me just say as much as I can. So the first thing that Haldane did is that the overall magnetization is 0 in the ground state. So that we already know. But
Okay.
it turns out that there's a staggered magnetization, because roughly speaking, the spins do point up, down as you go along the chain. So the first thing he did was to define this staggered magnetization. It's a vector, but it's a staggered magnetization. So it is -1 to the n times the spin at site n, and you divide by the total s, so that this is like an unit vector.
Okay.
Okay. So then what he figured out is what is the something called the action of this. So because this is a theory of a one-dimensional system, this phi, you can think of it as a function of the position x on the chain. So that's one coordinate, the x coordinate, and time. So it turns out that the action has a form like this. This is actually the same action that you see for a wave equation. It's got second derivative in time and second derivative in space. But there are two parameters here. There's a velocity v, and then there's a g, which is the strength of the interactions, it turns out. Then it turns out, so the first part was actually quite simple to guess, that there's a del phi by del t squared, which is like the kinetic energy, del phi by del x squared, which is like the potential energy. The important discovery of Haldane was that there's another term in the action, which is a little hard to visualize. So it's phi, it's like a triple product, phi dot del phi by del t cross del phi by del x. Okay. And the important thing is that this coefficient in front, this theta, he showed is 0 if the spin is an integer and pi if the spin is a half-odd integer. Okay, so it is kind of quantized, that it's the same value for all integers, and which is 0, and it's a different value for all the half-odd integers, which is pi. So it turns out that this term that he discovered, it has a topological significance, which is that, suppose you think of space-time x and t. This is, you think of it as a large plane, right? It's two-dimensional. Think of it as a large plane, and let's you can wrap it up. There's something called a stereographic projection. Like you can take a complex plane and wrap it up onto the surface of a sphere by doing a stereographic projection. So the space-time, you can wrap it into a sphere. On the other hand, this phi is a unit vector. So you can map all possible unit vectors phi to the points on a sphere. So you have two spheres now. One is the sphere of space-time, which you have wrapped into a sphere, and the other is this order parameter phi. This is the local order parameter phi, the staggered magnetization. That also is the surface of a sphere. So it turns out this object that Haldane found is actually the wrapping number of the sphere of space-time to the sphere of phi, and is therefore always an integer.
Okay.
Okay. Okay. So the next thing that happens is, sorry.
Yeah. Please go ahead. Yeah.
Yeah. So next thing is that now you think of a picture of a configuration of the staggered magnetization. Let's try to picture one, which is wrapping number 1. So the way you'll get a wrapping number 1 is if suppose phi points in the minus z direction in the middle and points in the plus z direction in the infinity. So you have to visualize this as you're going out from the origin towards infinity. The spins are gradually turning from down, they're turning up, so that eventually when you go to infinity, they're all pointing up. So if you think of wrapping this now on the surface of a sphere, you'll find that at the south pole of the sphere, spins are pointing down, and the north pole of the sphere, they're pointing up.
Okay.
So it is basically, you're wrapping around the sphere once when you do this. Okay, so this is an example of a wrapping number 1 configuration.
So basically, this is due to the different topology of because of the value of spin.
Right, because the spin configuration is this way, that it has one value in the center and a different value very far away. This has a topological structure. It's really exactly like a vortex.
Yeah. Okay.
Okay. Now, now in the previous thing, you saw that there is this term theta, e to the power I theta times this topological term. And so configurations with wrapping number w, they'll contribute to this partition function z with an amplitude e to the I theta w. Okay. So that was Haldane's contribution, that he found an extra contribution to the partition function of the system, which is e to the I theta w. Now, now for integer, half-odd integer spin, theta is pi, and configurations of phi with even wrapping numbers contribute with amplitude +1, right? Because you have I pi times w is even, so that's +1. Whereas if you have an odd wrapping number, w is odd, theta is pi, you get -1. So you see that configurations with different wrapping numbers, odd and even, they cancel each other. So there's a kind of destructive interference between configurations with different values of this w. And because of this, the excitations are gapless. Now the last part is really hard to prove because this is after all a kind of field theory. Why should interference give rise to gapless excitations? So let me give you a very simple kind of analog of this. So suppose you think of a double well potential in quantum mechanics. Imagine that normally you have tunneling between the two wells, and because of the tunneling between the two wells, there is a splitting. There is a symmetric state which goes slightly down in energy. There is an antisymmetric state which goes slightly up in energy. But suppose for some reason there was some destructive interference which prevented tunneling between the two ground states. Okay? So suppose that the tunneling was actually 0, then the ground state and first excited state would be degenerate, and you'll have no gap between them. So this is a very simple example where destructive interference, where you don't have tunneling, can give rise to gapless situation where there's no gap between the ground state and the first excited state. So this is what happens for half integer spin, theta equals pi. So the excitations are gapless. So the excitations are spin waves. So at certain momenta, the spin waves have 0 energy. For integer spin theta, so now you see if theta is, for integer spin, theta turns out to be 0. And so you can see that this topological term doesn't play any role, because no matter what w is, whether it's even or odd integer, this is always Theta is 0, so there's always 1. So all configurations of theta contribute with the same amplitude. There is no destructive interference. And then it turns out that the excitations are gapped. So this is the big difference between integer and half-odd integer spin, that because of this topological term, there is interference, destructive interference for half-integer spin and no such interference for integer spin. Yeah, so that's the way Haldane found this difference between integer and half-integer spin.
Oh, thanks, Professor Diptiman. Yeah.
Sure.
Yeah.
Thanks, Professor Diptiman, for an excellent talk.
Okay. Thank
Really,
you.
it was complicated, but it was very, very interesting.
Yeah, thank you.
Thank you very much.
Yeah, so I'll actually send you my talk as a PDF file, and you can share
Yes,
it.
okay.
You can
Okay,
share
sir.
it.
So anybody has any other query? Madhukar, you want to ask anything or you just?
No, fine. Okay.
Okay. Last one question we can take if.
Okay.
So it seems there is no further question or query. Once again, on behalf of the physics department, I'm thankful to Professor Diptiman Sen for giving this wonderful talk on very complicated topic, and we are definitely enlightened by this talk. And in future, we would be happy to receive you physically in BIT
Okay.
Pilani.
Yes.
And we would be happy to, we would be very happy to listen a series of talks on this
Okay.
Yeah,
particular
sure.
subject.
Okay.
And
Yeah.
when I was a PhD student, Professor Diptiman gave a talk in Sir School at HRI.
Oh, right. Oh, on this topic, is it?
Not on this topic.
This Haldane spin chains?
Yeah.
Okay. Anyway, Bosenization maybe.
Yeah.
My colleague Professor Naveen Singh is not too young.
Okay. Yeah.
He might have attended this school maybe 13 or 15 years ago.
It was 2001, I guess, or no, 1999. I think last century it was.
Okay. Yeah.
I'm sorry, I have given a hint of your age.
So that time it was called Mehta Research Institute.
Oh, right.
Right.
Yeah. So I think maybe Sumati Rao was the organizer.
Yeah, Suniti Rao was the organizer. Yeah.
Yeah. Okay. Now I remember.
Yes.
Yeah.
It
Yeah.
was, I think, first CRC school on statistical physics,
Right. Okay. Yeah.
field theory and statistical physics, something like that.
So, Professor Diptiman, if you are around Pilani, maybe in Delhi or some,
Yeah. Sure.
you just write to us.
Yes. Sure.
And if you are free and the situation is favorable for hosting you in Pilani from the pandemic situation,
Sure. Yeah.
we would be very happy to host you.
Yeah. I look forward to it. I haven't, as you can imagine, I have not gone out of Bangalore for more than 2 years now.
Yeah.
So I look forward to traveling again. Yeah. I'll certainly contact you then.
Yeah.
Sure.
So, thank you very much again. And
Thank
with
you.
this, I formally close this talk.
Okay.
And you can share your entire slides.
Yeah. I'll do that right away. I'll send you the PDF file.
Yeah. Okay.
Okay. Thank you very much. Yeah.
Okay. Bye-bye.
So I will send the recorded lecture to you, and with your permission, I will put on the YouTube channel of Physics Department.
So YouTube can be accessed by anyone, right?
Yeah. Yes.
I mean, even people outside Pilani can access.
Yes. It will be publicly accessible.
Oh, that's good. Okay.
Yeah.
That's nice. Okay.
Okay. Thank you.
Thank you. Okay.
Okay.
Bye-bye.
Thank you. Bye.
Bye. Yeah. Okay.